Hi everyone. So today I'm going to talk about Wasm3, which is a really fast WebAssembly interpreter. But first, I'd like to tell a few things about myself. So I'm co-founder of Blynk. Blynk is one of the most popular IoT platforms in the world. It's currently used by more than 700,000 people all over the world, like developers, small companies, bigger companies, and even enterprises. And I'm kind of a product development guy, so I usually tend to think about how to develop the product, how to ship it, how to package it, how to which features of the product are more likely to be used. And I'm also a hardware enthusiast, so I love to tinker with different hardware, like Arduino stuff, Raspberry Pi, and other things. Actually, I have quite a lot of hardware, and my main expertise is hardware related. So I've been in embedded software development for more than 10 years already. And I have lots of pet projects. I love to dig into technologies. I love to try out new things. So yeah, naturally, I'd like to present you with some piece of hardware, which is BBC Microbit. BBC Microbit is kind of an Arduino-like platform. It's really simple. It has a small processor which runs on 16 megahertz. It also has a little bit of RAM, just 17 kilobytes of RAM, and also 256 kilobytes of flash. Flash is used to store the program itself, like the machine code. RAM is used to hold data throughout the execution of that program, and CPU is used to actually execute those commands. One interesting thing about BBC Microbit is that it also contains Bluetooth Low Energy support. We're not going to use that today, but it's really interesting. So what I have on my desk is a small demo with BBC Microbit. It's not very complicated. It's just, some kind of an LED strip animation. And I can use button to change the animation. So we have some colors changing, and we have this kind of a wave function. Yeah, nice. One reason why it's so dark here, because I couldn't get the LED strip to be displayed correctly on this video. It's really hard to achieve, so I had to dim lights. Yeah, it's not too interesting unless, what if I tell you that this thing is running on WebAssembly? So the animation itself, the button handling, and well, just the whole demo is running on the WebAssembly, and it's running on assembly script. I'd like to show you how it's working. But first, let's look through some code. So we have this kind of project. Great. So it's a platformia project, which consists of WebAssembly virtual machine and also of assembly script program, which is actually running the animation. So let's take a look at assembly script file. So we have some kind of buffer for LEDs that will be allocated in the memory. And then the virtual machine will be using this memory to access the display buffer. So it's actually like a display buffer for LED strip. We have some like helper functions to basically convert colors and other things. And we print some stuff. And we have some several animations here. So the general idea here is that we fill the buffer with some values, and then we just call RGB show of some dev object. But what it is, this device object. So it's imported from Arduino TS. Let's open it up. Arduino TS, it's just a helper module which maps these specific functions to the to native functions in the virtual machine, right? So we are not using Wasi or any kind of standard APIs, but we implement our own interface, which allows us to control the LED. And if we take a look at the virtual machine, we'll have a bunch of what we call raw functions in Wasm3. So those functions are directly mapped to some Arduino API you may be familiar with. So like milliseconds or delay functions are directly mapped to the WebAssembly functions. And if we take a look at RGB show function, it's really simple. It just collects all of the colors from the virtual machine. It uses NeoPixel library from Arduino to set those pixel colors to the LED strip, and then it shows it. So basically, this is a kind of a driver for LED strip, which implements this particular LED strip functionality, and this functionality is exposed to WebAssembly. So by implementing these kind of simple functions, we can map and directly access different functionality on the hardware directly from the WebAssembly. Yeah, we can basically build it. And well, basically, yeah, we can change some stuff in the animation. For example, we can change, oh, sorry, it's a WAT file. So we can change some stuff in the application itself. Yeah, like brightness, for example, and it will work. Okay, I don't think I have to run it right now, but let's move on. Actually, we can take a longer strip and test some performance with this one. So I took an 144 LED strip, and with a similar kind of hardware, I was able to achieve 24 FPS on this system. So I think it's pretty practical, and it can be used right now. Another interesting example of running WebAssembly on embedded devices would be a Game of Life demo on K210, which is a 64-bit RISC-V processor. It's written in assembly script, and it looks something like this. So in this case, we have the same application running both on the laptop and on the device, and it's well, basically it runs much slower on the device, but it's the same Wasm file. So with all this, I think we are going to cite the same tweet by Solomon Hykes, which is already which was already mentioned today. But the interesting part of it is, how did we get to this point, right? So around 2 years ago, I knew nothing about WebAssembly, but I'm really interested in virtualization on embedded hardware, because my business is related to IoT, and we have loads and lots of different devices. They are very different one from each other, and we'd like to unify things somehow. And yeah, naturally, WebAssembly looked like a good solution to containerize, to somehow unify this interface. So I started, like a year and a half ago, I started my personal effort to implement an interpreter which would work on this kind of devices. Unfortunately, I got distracted by some other projects. So yeah, as I said, I have a lot of different pet projects. So I got distracted, and I couldn't finish this. So it was, for me, it was really hard. I mean, it looked really big, and eventually I canceled it. But after some time, I found that that nice project, which was Messy Meta Machine by Stephen Messi. I was really excited to find it, and I tried to run it on my machine. I tried to port it to different devices, and interesting thing here is that it wasn't really complete. So at this stage, it was just prototype. So I had somehow to make it useful to run real WebAssembly applications. So I contacted Steven, and we started a joint effort to bring his prototype to a more mature stage where we can run Wasi application, for example. So first we started by implementing the specification test. So we converted the official specifications test to JSON format, and then we created a Python script which was able to run our engine and to test it against the official specification. Yeah, it was really interesting because as we were getting closer and closer to the full spec test compliance, we also wanted to run some real application, and Wasi was really interesting option because we could use existing tool chains, existing infrastructure to build those apps and to try it out in our engine. And especially I was interested in this because we wanted somehow to understand how to measure the performance, as Wasm3 was positioning itself as the fastest interpreter out there. So we had to prove it somehow. And there is, like, embedded world. I know about CoreMark. CoreMark is a pretty standard test to run on different devices to test how much performance does it. Well, basically, to test the device performance. So I decided, why not trying to run CoreMark on the WebAssembly itself. And we ported CoreMark to the WebAssembly. And eventually we were able to run it in our engine, and we showed some really good results on that. At this stage, we are considered the fastest WebAssembly interpreter. Then also it was necessary for me to the whole project itself is kind of research. So I'm trying to squeeze as much as possible out of WebAssembly, running it in different environments, especially. So I was wondering, what about running it under different architectures? So we tried running it on Arduino, on MIPS systems, and also on Extensa, which is maybe you are familiar with this, like ESP32 or ESP8266 devices are Extensa architecture. And also, if we're running on C, why not running it under WebAssembly itself, right? So we also did that. I'll tell later more about the outcomes. Yeah, after all this, we got really bored, and we also tried to implement big endian system support. So big endian systems are treating multi-byte values in a different way, kind of reversed. And WebAssembly specifically is designed to work on little endian systems, but big endian systems would require a lot of byte swapping to make it working. And we found an interesting approach where we can just convert the linear memory layout to little endian while working on the big endian system, while the native stack is still laid out in the big endian layout, because actually the WebAssembly internal stack, like the WebAssembly stack itself, is not available to the application, so it has no side effects. The layout of this stack that makes no impact on the application execution. So we only convert what is visible to the app, and it's actually enough to work on the big endian systems. And currently, we are slowly implementing new WebAssembly proposals. it's pretty convenient because as it is an interpreter, we have only a single source source code. So whenever implementing new functionality to the interpreter, it's automatically available to all of the systems that we support. I mean, all architectures, almost all microcontrollers and other platforms. So it actually having an interpreter is actually a big benefit for us because of this convenience, right? But what's actually an impact of this? Because yeah, it's all nice. We did so many interesting things with WebAssembly. And actually, as I said, Wasm3 is kind of a research project. So by trying this, we are evaluating the current state of technology. We are trying to understand if it's usable for embedded stuff or IoT, for any kind of things. And it's interesting because we actually found some pitfalls. We found some inconvenience in the WebAssembly as it currently is. Anyway, nothing crucial, nothing too critical. Everything works fine. And one of the questions that we are going to answer today is, how do we even fit in 16 kilobytes of RAM? Because WebAssembly is currently using 64 kilobyte pages. So if you want to allocate a single page, you'll have to allocate 64 kilobytes of RAM, which you don't have. On Microbit, we have only 16 kilobytes of RAM. So actually, it was quite a big issue in the beginning because interpreter was working according to the spec. It was passing all of the spec tests and, well, at least pretending. So it was indeed an interesting challenge how to resolve this situation. And actually, what we did was to try to use compiler's infrastructure to get out of the situation. For example, if you take a look at this picture, you'll see that, for example, in the linker of LLVM, you'll notice that you have stack, which is growing downwards, and the heap, which is growing upwards. And usually, this heap will have some maximum memory. And the way compilers work and the way the support libraries for most compilers work will be that this maximum memory will always align to the actual linear memory which is available to the WebAssembly module. But what if we could just limit it somehow? What if we could allocate less heap for a WebAssembly module, which is even less than a single page of WebAssembly? And that's exactly what we did. We contacted several compiler support engineers, and we tried to figure out how to do it on different compilers. So assembly script was tweaked easily. Well, we added just a few functions for the compiler itself to be able to squeeze this address space, and everything worked thanks to Max Gray, who coordinated this process. For TinyGo, we just created a few tickets on the GitHub, and the community just helped us. We resolved a few issues. Actually, I was lucky because TinyGo was kind of going through some improvements at this stage. They didn't work on the project for some time, and then somehow the process resumed, and we just jumped in the right time and also implemented a few things in TinyGo, which also supports now those tiny microcontrollers on the Wasm3. For C++ and for Rust, we didn't experience any major issues, except that we had to find the correct command line arguments to make it working. So yeah, pretty cool. All these compilers are feeling fine in these kind of constraints. And after that, we started to implement more complex functions. For example, if you are running Wasm3 on the WebAssembly, then the interesting question is, how do we run Wasi applications under the interpreter inside of the Wasi environment? So here you can see that we use WebAssembly.sh, which implements Wasi environment in the browser. So it's totally running on the WebAssembly. And we run Wasm3, and we run Wasmer Boy, and then we run a game on the Wasmer Boy. So it's like having two virtual machines, one of which is native to the browser. Then we have an Wasi we have Wasi emulation layer provided by WebAssembly.sh, and after that we have Wasm3, which tries to transparently map Wasi calls to the host, like to the environment that is running in. And that actually works. So it was an interesting experience of how can we provide complete Wasi support for applications running on the emulation. And yeah. Also, another question was, what if we try running WebAssembly or like Wasm interpreter on the itself? So actually, after a bit of efforts, we were able to show complete WebAssembly and Wasi self-hosting, which means we are running Wasm3 on the Wasm3 either without Wasi or with Wasi interface, and also at the same time we are running another application on the two layers of emulation. Why do we want to do that? Or actually, for me, it's kind of a stress test. So it's not a very good performance test, but it's a good stress test. And as for me, it displays the completeness of implementation. The interesting part is that it was only possible to perform after we invented Meta Wasi interface, because actually having emulating the whole Wasi interface on the WebAssembly was impossible. I'm not sure if it's, well, basically Meta Wasi solves this problem. Also, while developing Wasm3, we were facing some situations, difficulties, because, imagine that you are trying to run a program, like something more complex than Hello World, and it fails. Debugging Wasm is really tricky, and we found that interpreter can be used to provide more debugging facilities to WebAssembly itself. Trying to figure out why core mark fails, or trying to figure out what happens with what's wrong with our Wasi calls at all. We tried to build a tool that will allow us to track those calls, to understand what's the difference between a program which is run on the Wasi interface and, for example, on the host natively, right? So one interesting experience was to create an analog to strace utility. For those unfamiliar, strace is used on the Linux or Unix systems to track the API, like the API calls to the system. Like system calls, I'd say. So for WebAssembly, the closest things to system interface is basically the exported functions, right? So we'll have just to track which exactly exported functions are called and with which parameters, right? With which arguments. So in this case, we are showing that we are running Wasmer, and we run Wasm3 under Wasmer, which performs emulation of utils application. And then we just commanded to print hello world, right? So in this case, Wasm3 works as an strace utility on the Wasi environment, and it prints out all of the calls to the WebAssembly exported functions of these utils application. And then eventually, hello world is printed from the application itself, and then the application terminates. And yeah, having this information is really interesting. But what if we could do better? For example, maybe we can track calls, not only exported calls, but also internal calls of WebAssembly functions inside of the Wasi application. And that's what we did. And this is a sub-project, I'd say, a small sub-project of Wasm3, which you can find on our GitHub. It's called WasmTrace, and it's able to produce structured logs, like structured traces of a Wasi application execution. So in this case, we can see that, yeah, well, basically, it's a full trace of initialization of standard C library, and it continues like for a lot of pages. Check it out. It's a really interesting utility, and I think this kind of again, these utilities are mostly prototypes. So you're welcome to contribute. You're welcome to comment, create issues, or improve them. Another interesting project that we kind of were involved in was to combine Wasm3 with QuickJS and libuw, which is called TXJS. So basically, if you think about it, QuickJS is a JavaScript interpreter, and libuw is basically the same infrastructure which is used by Node.js to provide a synchronous operation. And Wasm3 is a WebAssembly interpreter. So by combining all those, we have something similar to Node.js with WebAssembly API enabled, right? So yeah, this is kind of a small and tiny alternative to Node.js. Check it out. Here is a link to the GitHub. So Wasm3 can be installed easily. On Windows, you can use a pre-built package from the releases, from GitHub releases. On macOS, you can just use brew install to get it installed. On Linux, you'll have to build it from sources, but it's just a few lines of code. And also, actually, we released an Arduino library for Wasm. So if you look for Wasm3 in Library Manager, you'll be able to find it. And Jonathan Berry was really glad to see that. He was waiting for 3 years to see something like that in the Library Manager. So I'm happy that we are able to provide this technology. I also see really big potential of this, and guys, please try using it. We are welcome to dive into this kind of stuff to complete this endeavor. And yeah, that's it from my side. You can fork our project on GitHub, and you can follow our Twitter accounts.